Okay, for problems 1 and 2, I'm going to show you the answers. And what I'm trying to show you is for f of -2, if you're looking at the graph, it is asking you to find x equals -2, and then look at what is the y-coordinate of the point on that line, and that y-coordinate is -8. And then you're doing the same thing with f of 0 and f of 3, looking at these other two blue arrows. Then for finding the value of x when f of x is equal to 6, with that, what you want to do is draw a line at y equals 6, because f of x is representing y. So I've got the line y equals 6. And then you're looking at what is the x coordinate of that intersection. So it intersects the line at x equals 5. So x equals 5 is the value of x when f of x equals 6. If you solved it through the equation, then you plug the -2 in right here. 2 times -2 minus 4 gives you -8. And then do the same for the other two. And if you're doing it with f of x equals 6, then you replace f of x with a 6, and you solve the equation. And while we're here, I want to point something out that while it's obvious to some of you, I want to be very, very clear. There we go. Let me be very, very clear about the difference in the two directions. If I'm taking a number and I'm plugging it into the x of an expression, and I get 2 times -2 minus 4. When I do that, to find the number, I go through correct order of operations, where I first multiply, get -4 with that, and then I do addition, subtraction, and bring these together to get -8. But when I'm solving equations, I'm going from the y backward to the x. So if I'm going backward, I'm actually doing the opposite order of operations. Anytime you solve an equation, that's actually what you are doing. So with order of operations, multiplication comes first, addition, subtraction comes later. So that means the subtraction is the weakest PEMDAS operation. It is the first one to undo. And we're going to be talking about that as we go through this unit. This unit is all about inverse functions and understanding the issues with inverses. And then divide by the 2 to get 5. With the second one, similar issues, but I want to point out to you these 3 different situations with solving. When you're looking at the graph, if you draw the line y equals -2 right here, it crosses the graph of this parabola twice, once here and once here. The x coordinates are -4 and 0. And that's how you can solve equations when you look at a graph. For the next one, when you draw the line for y equals -6, you want to notice that that line only crosses the parabola once, and the x coordinate is -2, and it has only one solution. And then lastly, I want you to see that if you draw the line y equals -8, it does not cross the parabola, and that means there is no solution. And it's very, very, very valuable for you to understand the relationship between solving equations with a graph and solving equations given an actual equation, where for this particular problem, if you replace f of x with -2, if you were to solve it through the equation, you would need to do backward order PEMDAS, which means our weakest PEMDAS is subtraction. We will first add 6. And when I add 6, I will get 4. And now parentheses is a strongest operation. Exponent has to be undone before what's in the parentheses is undone. But there's an unfortunate little extra bit here. When you take a square root, you have to remember plus or minus. But since we are looking at the graph here while we are looking at the equation side by side, the problem with needing that plus or minus is the issue that this graph does not pass the horizontal line test. The horizontal line test is the idea that if I draw any horizontal line, if any horizontal line crosses the graph more than once, I have the potential of getting more than one solution when I solve the equation. When it comes to a parabola, you have two sides of a parabola. You have a positive or right side, and you have a negative or left side. And it is those two sides that are creating the plus and the minus. And if you don't do the plus or minus, then if you look at the graph, it causes this half to just float into space and disappear. So it helps to see the graph and the equation together to genuinely understand why you need that plus or minus. And we're going to be talking about this issue more in this unit. So, yes.
It doesn't pass the vertical line test, therefore it wouldn't be a function if you wouldn't just take one side. That's
right, right. If a vertical line crosses a graph more than once, then it's not a function. And when it's not a function, when you say, hey, plug a number into the function, what's my answer? You can't give just a single answer.
exactly.
Yeah.
If you're to say like, I want to like just put it in the context. If I said I wanted to buy a cheeseburger and it's like, oh, it's either $5 or $3.
Yeah. Yeah, it's a bit of a problem. So there's an important difference between functions and then the bigger issue when you aren't dealing with functions. Functions are nice because you know once you get that when you put something in, there's only one answer that can come out. Or you get that that it doesn't work. But that's why when you go backward, though, and you solve an equation, if it doesn't pass the horizontal line test, you have to be extra careful in solving. There might be more than one answer that you're dealing with. With the line passes both vertical and horizontal line tests. So that means that there's only one output for every input and one input for every output. And that makes it easier to work with. All right. So now, a lot of this is probably a review for you, so I don't want to go too slow and bore you to death, but I also don't want to go too quick if you need this. So I really need Are you guys able to see my presentation? Okay. Okay. So I really need your input on whether you need me to slow down or not. I'm going to try to go a little bit faster. Let me know if I need to slow down.
Does YAR stand for anything?
Yes, it does.
All right.
So normally we learn PEMDAS. I prefer PERMDAS because with PERMDAS you have P, MD, OS. You know parentheses. You also know that the E stands for exponent. Exponent. But what they don't tell you is that exponent and roots are opposite operations in the same way that multiplication and division are opposite operation. And in the same way that addition and subtraction are opposite operations. When it comes to opposite operations, they're on the same order of operations level. And the rule is if you have the same level of operation occur more than once, then you go left to right and do them in that order. But honestly, it's only those stupid internet things that they throw out there that are tricky. Have you guys seen that where they put up some bunch of stuff with parentheses and they're like, hey, what number is this? And everyone gets it wrong because they don't fully understand order of operations. Those are so stupid. But anyway, people somehow think they're so smart just because they know order of operations. That has nothing to do with intelligence. It has to do with, were you properly presented genuine order of operations? And did you retain it? Anyway, so I want you to be aware that exponent and roots, and I'm assuming you know what I mean by roots, but just in case, there's a root, but it's understood that that's a square root. If I put a 3, then it's cube root. If it's a 4, then it's fourth root. You guys have seen those before, correct? Okay. What is appropriate? When is it appropriate? Oh, you use it backward when you're solving an equation. You use it forward when you have just an expression. So if I had just what I highlighted right there, and I'm told the input x, and I put a number into that x. Let's say I put in -1. Then I'm going to go through forward PEMDAS. I'm going to first look at the parentheses here. Everything in there has to be dealt with first. Inside the parentheses, I have my multiplication and my addition. So proper order says multiplication first, 3 times -1. Then addition to give us the -2. Then the parentheses take place. And now I move on to, I have an exponent on that parentheses. And when I multiply -2 twice, I get +4. Then I do multiplication. Then I do subtraction. So that's if you are plugging a number into a function, into its expression, and just trying to find out what number that is. You go backward when there is an equal sign, and you need to figure out what numbers can I plug into x to make this equation true. You have to go backward to uncover that. So let me see what I wrote over here in the answers. So I've got important to realize with these three that each of these are pairs of opposite operations. And for the fill in the blanks, when solving an equation, each operation is undone in reverse order of operations with its opposite operation. And you've been doing that for a long time. You may not have thought about the fact that this is what you are doing. And we're going to keep talking about this and making more and more sense of it. That's what this whole unit is really more focused on. This unit is focused on reviewing a lot of stuff, but also making sure to solidify that you actually understand the algebra. People do algebra wrong when they don't understand. They've just been mimicking a process that they don't really understand why they're doing what they're doing. All of you can understand what we are doing, but I don't know if it's always really emphasized the issue of order of operations. That is the most important fundamental thing to genuinely understand. So here we go. When we solve an equation, what we're really doing is we're finding our variable. And then we are looking at, I think of it more as peeling the layers off the onion. And then I think about the Shrek movie, but you're looking at what is the weakest operation over there on the side of the equation where x is located. We have a parentheses, so everything inside of that is not going to be dealt with at first. With that aside, you have an exponent, multiplication, and subtraction. The weakest of those three is subtraction. So you are first undoing the subtraction by adding the 5. Then you stop and reevaluate what you have. Again, those parentheses are a done deal. They have to wait. You have multiplication and an exponent. What's the weakest of those two operations? The multiplication. You undo the multiplication through its opposite operation of division. And now you stop and you again take a look. You see a parentheses, and on that parentheses, you see a squared over the whole thing. Before you can go inside the parentheses and start undoing any of that, you have to undo the squared. This is the one thing that you have to remember a little extra on. And that's what I tried to talk about with the parabola over here when you are solving for these bottom problems. You will neglect half of a parabola if you don't put a plus or minus. And this is specifically when you take a square root. So I'm going to put a square root on top of both of those. And as I do that, I'm going to throw a plus or minus sign out in front of one of them. And then I notice that a square root and a squared undo each other. They cancel each other out. And the 3x plus 1 can now be released from its parentheses. With the plus or minus, that actually means I have two equations. For some of you, you can work with it as is with the plus or minus, but I'm going to write it as two equations. And then we'll solve both of those equations. At this point, with both of them, you have a multiplication and an addition. What's the weakest operation? Addition. So you first undo the addition by subtracting. And I'm going to do it to both equations while I'm at it. And then lastly, we divide. And we get two answers. All right. Moving on to example 4. Example 4, you have an equation with a square root, which means you're going to have to bring in the opposite operation of squaring. And I want to point out to you that when we did the square rooting in this step right here, when I brought in square rooting in green, I had to put a plus or minus sign so I didn't lose half my parabola. What you want to understand about solving equations with a square root is that you're actually starting with only half a parabola. And when you square both sides, you bring in the other half with it. That means you might have extraneous solutions and you have to check your answers. Extraneous solutions really only, and you guys have heard of that word before, extraneous. Extraneous solutions are when you think you're doing all the correct algebra moves and you get an answer and one or more answers actually aren't correct. What you want to know is you thought you were doing all the correct algebra moves, but there are some little technicalities that people usually don't stop and think about while they're making their algebra moves. And so you're taught that with specific types of equations, you have to check your answer. And I want you to understand that there's a reason for it. And it's usually easier to see visually what the reason is for it. And like I said, it's the issue of the parabola having two sides. We're going to look at graphing the square root function and as well as the parabola today. When we look at the square root graph, I'm just going to throw this out there real quick. Your square root graph looks like half of a sideways parabola. When you take an equation that is a square root and you square both sides, you create a bottom half that didn't exist, a phantom. It's like a phantom leg, I guess. You feel it, but it's not there. Sorry, didn't. That sounded kind of dark. But that's what's happening with extraneous solutions. So here we go. I want to look at where my variable is. Actually, first thing, I want to point out you have an equal sign. When you don't have an equal sign, you aren't solving an equation. When you have an equal sign, that's when you want to identify your variable. And if there's only one variable sitting there, then it's a kinder equation. And your job is to isolate that variable by slowly undoing with backward PEMDAS. Here we go. When I look at this expression, I don't know if you're fully aware of this, but when you have a square root, there's an understood parentheses that nobody ever talks about. And people make a lot of mistakes with square roots because they don't realize that there is a parentheses that we never write in there, and I think that is a terrible thing that has been done. There are a lot of choices that were made with math notation that I think are terrible choices that make people think they're bad at math, but really they just don't understand what is unsaid and unwritten, but just understood. And that's unfortunate. So you've got to remember that there's always a parentheses under a root, and you've got to think about it that way. That makes that subtraction too strong to be the first thing to undo, or to even undo it until the very end. Now, what you have here is a root and a division. And just going back to the issue, root is on the same level as exponents, and then division is a lower level on PERMDAS. That means I'm going to first undo the division. And I undo division by multiplying by 3. And then once you do that, you stop, you look at what you have. You want to remember that there's a parentheses here. That subtraction is too strong, cannot be split up right now because it's not a subtraction, it's a parentheses. So I undo the root by doing the opposite operation of exponent, and it's understood that there is a 2 here. We just don't write it. Another thing that ends up confusing people. And I square both sides. I don't put a plus or minus down when I square. I put a plus or minus down when I take a square root. So now on the left side, I have x minus 8 in parentheses, but the parentheses can come off now because nobody else is there. 6 squared gives me 36. And then the last thing I need to do is undo the subtraction by adding 8. And then 36 plus 8, 44. Now, you want to know what's an awesome quick way to determine if this is extraneous or not without having to go through too much work. The issue with square roots is that you cannot take a square root of a negative number. Bad, bad, ah! What that means is the expression under the square root must be positive. It can be 0. If I plug 44 into this x, will I get a positive number? And I just noticed some stuff in chat. You don't need to do any more work. You're good. That is literally all you have to do. It's an issue. You just have to know where the problem lies. And that's the issue that you cannot have a negative number under a square root. You don't have to go through all of the arithmetic. But do keep in mind you have to check your answers when square roots are in your equation to begin with. Okay, so I'm going to go through graphing a little bit quickly. Let me know if I'm doing it too quickly. For absolute value of x, you should know that that makes the V graph. When x is positive, the absolute value is meaningless, shall we say, and you are really just getting the line y equals x. But when x is a negative number, what was going to be the continuation of the line y equals x has to be reflected over the x-axis, giving us the V shape. So when you see the absolute value of x, you need to know that it creates the V shape where your lines have a slope of -1 and +1. And I'm, again, just going to throw this out pretty quickly because you should be aware of these things already. The domain is just asking horizontally, does this graph cover everything horizontally? Does it exist horizontally everywhere? Yes. So we use interval notation and say -infinity to infinity with round brackets. The round brackets means that there isn't an end to that interval. For the range, you're looking at vertically, does the graph exist everywhere vertically? And it only exists for y equals 0 and higher. You do a closed square bracket on the 0 because it's an actual point that is an endpoint, and then to infinity. And then the vertex is 0, 0. And I'm not going to worry about filling out the table. It's just to emphasize an understanding of the graph. Now, for sketching 1/2 multiplied by the absolute value of x, perhaps you remember that multiplying by outside the function either squishes or compresses or stretches the graph. What it really does is it takes all the y values and multiplies them all by 1/2, which would be dividing them by 2. So that causes your graph that was going at a 45-degree angle and was going through the point 2, 2. If I take the y-coordinate 2 and I multiply it by 1/2, I will get a y-coordinate of 1, and that will help me to see where that line goes. And I can actually do that for any of those y-coordinates. I can multiply them by the 1/2, and that will tell me where it got squished or compressed or stretched to vertically. And what I'm doing here is I'm presenting a two-step process. In the next graph, I have the same 1/2 multiplying. That means that I'm starting with this graph. After you deal with the multiplication transformation, then you do any addition, subtraction transformations. And you probably remember this. This tells you you are vertically going to move down 4. And you always have to do the opposite of what you see there. You see -3. Horizontally, you are going right 3. And the issue, I may have to wait to say more about this because I'm looking at the time. But I will continue to talk more about what's going on with why you go the opposite direction horizontally, where the vertical addition subtraction, you do the direction it says. What you're going to do is take your vertex, move your vertex down 4, right 3, and then let the graph open up the way that it was when you multiplied it by that 1/2. And I'm trying to draw it decently. Now, the domain is -infinity to infinity no matter how I change this graph. When I do the multiplication, as long as I'm multiplying by a positive number, the range will not change. But when I vertically move the graph, that will cause the lowest point to change. Now the lowest point is -4, and then it goes to infinity. The vertex will not change with multiplication even if you multiply by a negative number. The vertex will only change with your movement. And I went right 3 and down 4. My vertex started at 0, 0, so I can literally just write down what those two transformations were. Now, you guys are familiar with the graph y equals x squared. I have found that you guys usually don't have an issue with it. What I'm going to do is after class, I'm going to continue the video and talk about the x squared in case you need it. You can look at that video later and get that information. For the square root of x, you need to understand you cannot plug negative numbers in, and so that is undefined. If you plug in 0, you get 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, and that gives you some nice points to plot. And with square root being the opposite of squaring, there's a reason that this looks like half of a parabola, or at least I should say, there's a reason that it looks like a parabola. So I'm going to plot these points. At least plot the points that are still on the map. So I cannot plot the point 16, 4 on this grid. So I just plot these. And it is a partial inverse of x squared that's really important to be aware of. The domain, it includes 0 and goes to infinity. The range includes 0 and goes to infinity. The domain is the horizontal existence. The range is the vertical existence. If I multiply by -1, that multiplies all the y values by -1. That causes the graph to reflect over the x-axis. You might remember that. However, where y is equal to 0, multiplying 0 by -1 won't change it. So that point is still there. Now, I have this again as, I can't think of the word. It's a continuation. I have that multiplication by -1 over here. The only new thing is the +2 and the -3. That means that I'm taking this graph and I am moving it down 3. And when you see the +2 with the x, it's not horizontally moving in a positive direction. It's actually horizontally moving in a negative direction. And we're going to talk about that as we go through the unit. So left 2 units. It's easiest to move the 0, 0 point. Left 2, down 3. And then you can either individually move the rest of them or realize kind of the pattern that it takes on. And I'm trying to just quickly throw that out there. Okay, domain. The domain with just multiplying by the -1 is still 0 to infinity, but the range changes. Vertically, this graph now exists 0 and below. I have to write my interval notation in an order of the smallest is negative, super big, negative, through the negative numbers up to 0, and then it ends. The end point is 0, 0. And I want to emphasize that this is a notation for a point, and it unfortunately looks a lot like in the interval notation. And those are things we're going to need to talk about, and I'll clarify with you. Then I have over here, with the movement, that will change domain and range. The domain is now starting at -2 and going to getting bigger. The range has its highest value at 3, and then it is lower than that. So I have to write it in that specific order. The endpoint is -2, -3. For graphing the function y equals x squared, that is the parabola that you're probably very familiar with. The vertex is at the origin. And if you plug in 1 or -1, you get 1 out. If you plug in 2 or -2, you get +4. If you plug in 3 or -3, you get +9. The domain is all real numbers. So that means from -infinity to +infinity. But vertically with the range, it only exists where y is 0 and then positive. So I include 0 and go to infinity for the range. And then the vertex is the point 0, 0. And I do want to point out that the notation on these two that I just highlighted both have round parentheses. Anytime you have round parentheses with a comma in the middle, you have to look at the context to decide if it's representing a specific point. For example, if, let me go this way. If I plot this point, I write -4, 2. But when I write -4, 2 as an x interval, like if it were representing a domain or a range, that's saying on a number line where you have 0, 1, -1, 2, -2, and all that, that not including -4, but everything larger than -4, and not including 2, but smaller than 2, that all of those numbers are part of either an answer or a domain or a range, and that's different from a point, even though it is written the exact same way. So it's all about context when it comes to that notation. When I multiply by 2, I take all of my y coordinates of the original graph and I multiply each of the y coordinates by 2. So that means right here where I have y coordinates 1, I will then have y coordinates 2. Where I have y coordinates 4, 4 will be multiplied by 2, and my y coordinates will be 8. And I just realized I plotted that in the wrong spot. And then the vertex has a y coordinate of 0. 0 times 2 is still 0, and that will then stay right where it is. So when I multiply a function by a number larger than 1, I cause it to stretch up vertically. Kind of like, hate to say it, but little torture devices with the stretching rack, kind of like that. But if I'm multiplying by a number that is between 0 and 1, I'm actually compressing or squishing it vertically down, as I did with the absolute value. And when you multiply by 1/2, you could also look at it as dividing by 2, because they are exactly the same thing. So realize that with your transformations, whatever is multiplying or dividing to the function, you're going to take the y coordinates and just do that to those y coordinates. Multiply by the 1/2, multiply by the 2, and in this case down here, multiply the y's by -1, and that will force the reflection if you multiply those y values by -1. Then over here, I still have the multiplication by 2, but what changes from this first transformation to the next transformation is dealing with the addition or subtraction if it were subtraction. The addition outside the function, addition or subtraction outside the function, moves it vertically, and it changes all the y's by adding 1 to all of the y's. It will move the graph up 1. When something is added or subtracted directly to x, you actually have to do the opposite operation. So when it says add 3, you really need to subtract 3 from your x coordinates, which will cause you to move the graph left 3 units. The easiest thing to do is to move the vertex and then sort the points out from there. Or you can literally take each individual point and move each individual point. So moving the vertex up 1, left 3. And then if I look at the relationship, this pair of points is horizontally 1 unit away, 2 units above. These pair of points are horizontally 2 units from the vertex and vertically 8 units up from that vertex. The vertex 2 to the right, 8 up. 2 to the left, 8 up. And then draw. The domain, as long as I multiply by a positive number, or sorry, I'm thinking range. The domain of your parabolas are that they always exist everywhere horizontally because it is moving to the left just very slowly and to the right, but just very slowly forever. So the domain is -infinity to infinity. The range, as long as I multiply by a positive number, not a negative number, it will remain 0 to infinity, including 0. And the vertex will not change with any multiplication by a positive or a negative number, because the y coordinate of the vertex is 0. Multiplying anything by 0 will not change 0. Over here, where I've shifted everything, my domain is still -infinity to positive infinity. My range, however, by shifting everything up 1 unit, my now lowest y value is 1, and then it goes up from there. My vertex can be found just by looking at the movement, left 3 and up 1.